Hi, thanks for joining me. Today I'm going to be going over problem 3 from week 4 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details about the competition. Anyway, this is a problem I'm going to be going over today, and as you can probably tell, it's a geometry problem. I haven't written out the problem in full, so if you want to see a full statement of the problem, I'll leave that in the description as well. Anyway, we have a triangle, ABC, and we draw a circumcircle around it. So a circumcircle is simply the circle which passes through each of the vertices, and that's a unique circle. Okay, and O is the centre of this circle, so this point here. Now we have that K lies on the line AB, so K is there, lying on AB, and L lies on AC, so L is there, and we have the property that KOL is collinear. So in other words, if you draw the straight line through K and O, if you extend that, you'll also pass through L as well. We have that R is the midpoint of BL, so this line here, BL, R is the midpoint, and we have that S is the midpoint of CK. So CK is here, and S is the midpoint there. What we want to do is prove that the angle BAC, so this angle here, is the same as angle SOR. So this angle here, I hope you can see that. So between S, the origin, and R. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so there are actually a few different ways you can solve this problem, but the way I'm going to be showing you uses as little geometry knowledge as possible, simply because I'm not the biggest fan of geometry myself. I'm more into kind of algebra and stuff, and that's kind of what I'm going to be doing. I'm going to be using complex numbers to solve this problem. Well, firstly, what we can do is let our origin O just be the origin of a complex plane, and we can also assume, without loss of generality, that our circle here is of unit radius. So we're working on the unit circle. And the reason we want to do that is because these points on the circumference here, they're now complex numbers, or they're represented by complex numbers. What's quite nice about them is if we take their conjugate, so their complex conjugate, that's going to be the same as their inverse. And that holds for any complex number with unit radius. Its complex conjugate is its inverse. Anyway, what we're going to do is these guys here, these points B, A, and C, in fact all the points here, what I'm going to do is represent them with complex numbers, and I'm going to denote those complex numbers with lowercase letters. So the point capital A is represented by the complex number little a. This point here, capital B, is represented by the complex number little b, and so on. What we want to do first is write down what K is. So little k now. Well, little k here, well, to get to K, we can go from the origin up to A, so A, and then travel along this line here. So some lambda times b minus a. So here, lambda, we don't know what it is, but it's a real number, and we're going, essentially what this means is to get to K, we can go up to A, and then travel some lambda units in this direction here. Okay, like so. The next thing you want to do is compute K bar, so the complex conjugate of K. And this, just by property of complex conjugation, we can distribute it like so. It's just A bar plus lambda bar times B bar minus A bar, like so. Well, lambda, as I said, is a real quantity, so lambda bar just equals lambda. A bar, remember, because A is on the unit circle, A bar is just 1 over A, like so. And same thing goes for B as well, so I can write this as 1 over A plus lambda 1 over B minus 1 over A. But of course, 1 over B minus 1 over A is just A minus B over AB, like so. But now look, we've got lambda times A minus B in the numerator. But if we go back up to here, that's kind of what we have here. So lambda times A minus B is nothing but A minus K from this line here. So I can get rid of the lambda and the A minus B and replace it with just A minus K, like so. And this guy here, we want to put everything under the common denominator AB. So multiplying top and bottom by B for this guy here, we're going to get all in all that this guy here equals A plus B minus K all over AB, like so. So we've got K bar equals A plus B minus K over AB, and very similarly, using pretty much the same argument, we get that L bar is equal to A plus C minus L all over AC. Okay, so using the exact same argument, but with L now. Cool, we've got these two kind of equations for K bar and L bar. Let me clean up the whiteboard and we'll continue. Okay, so I've written down up here what we just proved. K bar equals A plus B minus K over AB, and L bar equals A plus C minus L over AC. The next thing I've done is I've written a claim, and that is that this ugly expression here equals 0. So we've got B times A plus C times little k minus c times a plus b times l minus b minus c times lk, that guy there equals 0. And the proof to this is just mainly algebraic. What we're going to do is remind ourselves that KOL form a straight line, KOL are collinear. So what that means is if we look at the ratio of complex numbers, K over L, this guy here is going to be some real quantity. So there are a few different ways of seeing this. Perhaps the easiest way is to write K and L in terms of like Euler's form, so something times e to the I theta, and notice that those theta values for K and L, they're going to have a difference of pi. So when you do one minus the other, obviously the e to the I thetas, you're going to kind of be subtracting one theta from the other. So you're going to be either left with a positive pi or a negative pi, but e to the I pi is minus 1 and e to the minus I pi is still minus 1. So it's going to be minus 1 either way. But yeah, these guys here, obviously minus 1 is a real number, so that means that K over L is a real number. Anyway, K over L is real, which tells us that K over L equals its complex conjugate. So this guy here just equals K bar over L bar. But then, of course, just rearranging this, we get that K times L bar minus K bar times L equals 0, like so. So just cross multiplying and then bringing everything onto one side. But then taking this equation here and then just multiplying through both sides by ABC, of course, the right-hand side will still say 0. You get this thing here, and then just using the things we just proved, these guys here, you know, it's just a bunch of boring algebra steps, but you arrive at the conclusion. So just plugging in what L bar and K bar are from this step here, doing some nice cancellations and factoring some things out, you're going to get this line here. So I'm going to consider that to be proven, because going from there to the final step is just a bunch of boring algebra. Anyway, let me clean up the whiteboard and we'll continue. Okay, so I've written up what we just proved in the top corner. B times A plus C times K minus C times A plus B times L minus B minus C times LK equals 0. The next thing I've written down are kind of two facts which we are going to recall now. The first thing is that for any complex numbers x and y, the angle XOY is equal to the argument of y over x. So if you've not seen this before, this is just kind of a standard property of complex numbers. Perhaps draw a picture and this will all make sense. But this is just a fact. And the second guy here, angle BAC equals half angle BOC, just falls from a circle theorem, or is just one of the circle theorems. So this angle here, BAC, which is one of the ones we're interested in, is equal to a half angle BOC. So if we go from B to O to C, like so. So that's what these two facts we're going to use, and we want to recall what our problem is. We want to show that this angle here, BAC, is the same as this angle here, ROS. So we want to show that BAC equals angle ROS, like so. But then, of course, BAC is just a half BOC, so I can write this left-hand side as just a half angle BOC, like so. But then we can just use our top fact, because both of these guys here, BOC and ROS, are in this form here. So BOC, if we just plug in x equals b and y equals c, the left-hand side just becomes a half argument of c over b. And the right-hand side becomes, when x is r and y is s, into this guy here, we get arg s over r, like so. But remember, arguments kind of behave like logarithms in the sense that we can bring exponents up to the top, and we can, when we subtract two arguments, it's the same as doing the argument of the two things divided. So if I multiply both sides by 2, I get a 2 here, but I can bring that into the exponent of this guy here. So I get s squared over r squared. And then, of course, bringing this arg c over b onto the other side, I'm going to get arg s squared over r squared minus arg c over b. But that's the same thing as just arg s squared over r squared divided by c over b equals 0. And then just simplifying this guy here, we get arg s squared times b over c times r squared equals 0. But of course, if the argument of a complex number is 0, that just means it's a real number. So essentially, we want to show that the guy in the brackets here is a real number. But from before, remember we had that k bar times l minus l bar times k equals 0, because k over l was a real number. Because we know this guy here is a real number, we get a very similar looking identity, namely s squared times b times cr squared bar minus s squared b bar times cr squared equals 0. And now notice that all of these steps here are kind of reversible. They're if and only if statements. So if we can prove this guy here is true, then we can track back and then deduce that angle BAC is equal to ROS, and that's our problem solved. So all we need to do now is show that this guy here is 0. Let me clean up the whiteboard and we'll continue. Okay, so we just showed that our problem has reduced to proving that this guy here equals 0. So s squared times b times a complex conjugate of r squared c minus the complex conjugate of s squared b times r squared c equals 0. So once we can prove that, that's our problem solved. And now, again, I'm not going to go and prove this in too much detail because most of it is just a bunch of algebra. So I'm going to give you the key steps, and if you want on paper yourself, you can verify that the details hold true. But the way we're going to prove this is similar to before when we wanted to prove that, when we wanted to derive this identity here, we're going to start with 16 times ABC times this quantity here, like so. Squeeze that in. So we start off with this guy here, and obviously 16 times ABC is non-zero, so if we can show this quantity here is 0, then that means that the guy in brackets will be 0 and we'll be done. And then if you just go from this guy here, then expand and write this as the difference of two squares, and then what you want to do is use we haven't used yet the definition that R and S are the midpoints of L, B and CK respectively. So that means that little r is equal to little l plus little b over 2, and similarly s is equal to little c plus little k over 2. So using that and plugging that all in, you're going to get something times this guy here, and of course that guy there is 0, so everything's going to vanish. So all in all, this guy here will just be 0. But I don't want to go through the steps because it is a bunch of algebra and I'll inevitably make a mistake. But essentially you just start from this line here, use the difference of two squares to start off, and then you're going to get two factors, and then you use the definitions of little s and little r as midpoints, and then just go ahead and crunch through some algebra, some cancellations and some factorizations, and you'll get something times that guy there, and of course that guy there equals 0. So you may have wondered why we proved that before, but hopefully now it makes sense why we did prove it. So anyway, I'm going to consider this proven. This guy here equals 0, which proves our claim, and then that solves our problem. So this angle here, BAC, is equal to angle ROS, like so. Anyway, I hope you have enjoyed today's video. Thank you for watching. I'll catch you in the next one. Have a great day.